I want to do an example now of uniform motion in one dimension. To review, uniform motion means there's no acceleration. We're at a constant velocity. And also we're limiting ourselves in one dimension to make the math easy. And in fact, this example is going to be quite simple because I have a bit of a larger purpose as well. So for this case, we saw before that we can write down the trajectory if we're on the x dimension. For this condition, x as a function of time is equal to the velocity in the x direction times time plus a constant x naught, where that is the initial position. Otherwise, the position at t is equal to 0. Also, we pointed out that if you're simply looking for 2 points in time, you can say that identify that as an initial and final point in time. You can say that the final position is equal to, or x sub f equal to the velocity times the time difference between those 2 points in time plus x sub I. Now this is true now in the x-axis. What happens if you're in the y-axis? Well, then you might write y of t is equal to v sub y plus y naught. You could have this, or in 2 points in time, you could have y sub f equal to v sub y delta t plus y initial. And then, of course, you could have the same thing for the z dimension. You can call those dimensions by different letters, which would get you more equations. The book by Knight, in fact, says, well, let's think about an arbitrary dimension, which we call s. So we have s of t is equal to the velocity in the s direction times t plus s naught. Or if we want to look at 2 specific points in time, sort of the final position, s is equal to the initial position s plus velocity in the s dimension times the time difference, where now s can represent x, y, or z, or any sort of arbitrary one-dimensional object. Well, so look what we've done here. This is now really quite a number of equations. There are, in fact, an infinite number of equations you might write down to describe this. This is a place where a lot of students run into severe problems because all these equations proliferate and they try to memorize all these equations, when in fact there is only one equation here. Which brings me to a very important point, which is never memorize equations with symbols, only words. Never memorize equations with symbols, only words. And what does that mean? If these are these equations here that I have, I would never memorize them by trying to remember x of t equals v sub xt plus x naught, x sub f equals v sub x delta t plus xi, because then you have to memorize y as a function of t equals v sub y, and you have to memorize all of them, when in fact, in words, there is only one equation here. How I would memorize that equation, how I would describe that in words is, for 1D uniform motion, the final position is equal to the initial position plus the velocity times the time interval. And this now applies everywhere. And I don't care how I write it down. I can write it down any way that's convenient to me. And so this one statement in words represents the infinite number of ways I can write that statement mathematically. And instead of trying to memorize the infinite number of ways I can write this down mathematically, I only have to memorize the words. And as human beings, we remember words a lot easier, and so it is in fact a lot easier to memorize sentences that describe things than it is hosts of letters and mathematical expressions. So when it comes to trying to memorize equations, trying to understand equations so you can use them, make sure that you always, for yourself, memorize them, or always learn them in terms of the words of what they mean, and never in terms of the symbols. Because the symbols can change, and you can change them to mean whatever you want. But what they mean physically in words never changes. All right, so let's use this in a simple example. I have a runner who passes the library going a constant speed at 6 meters per second. How much later does the runner pass the student union 240 meters away? Okay, so I'm going to picture here. I had the library. This runner was running past the library 6 meters per second, and 240 meters away was the student union. And how fast, how much later was it when the person passed the union? We're assuming they're running in a straight line. Okay, so first of all, I'm going to get now my schematic. I'm going to have a coordinate system. I'm going to put the 0 of my coordinate system at the library. I'm going to draw a straight line to the union. I'm going to call this my x-axis, and since it's a straight line, the library is at 0, then the union is at 240 meters. And so now I want to sort of identify and put into symbols what I know about the system. So I'm saying that at t is equal to 0 my runner is at the library, which is at x is equal to 0. So my initial position of my runner is equal to 0 meters. My final position, well, what 2 points in time am I looking at? Clearly, the 2 points in time I want to identify are the point when the runner passes the library and the final position passes the union. So the final position will be 240 meters. I know the velocity that the person has in the x direction running along this line, and that's 6 meters per second. And so what I want to find is the time interval, and that I don't know. Well, given how I relate uniform motion, I can form a relationship between these parameters. I know that my final position is equal to my initial position plus the velocity the person is going, v of x, times the time interval, delta t. And so I know 3 of these. I don't know 1. I have 1 equation and 1 unknown. And so that tells me I can solve this. So I have 240 is equal to 0 plus 6 delta t. And so my time interval is 40 seconds. Okay, So that's pretty simple. Let me do this again in, we'll say, a pathological coordinate system. Now, I have my library here, my union here, and I'm going to set at the origin of my coordinate system the athletic stadium, which is on a straight line between the library and the union, 1,000 meters away. Okay. I'm going to call my coordinate system, and I'm going to have my positive axis go the other way, and I'm going to call this my gamma axis. So if the library is 1,000 meters away and the positive axis is going in the other direction, in the positive gamma axis, my library is at negative 1,000 gamma. And the union, then, this is the library, this is the union. The union is at negative 1,240 gamma away. My person here is running in this direction. They have a magnitude of 6 meters per second, and they're running in the negative gamma direction. Okay, 6 meters per second. So if I want to identify these terms, I can represent them as symbols. So I can have my initial position, which I'll say gamma initial, is equal to negative 1,000 meters. My final position, which I'll call gamma final, is equal to negative 1,240 meters. My velocity, which I'll use for that, the symbol phi, because I don't care, I can use anything I want. Phi sub gamma represents my velocity. It's in the negative 6. It's in 6 meters per second in the negative gamma direction. And the time interval I'll call tau, is the time interval. Well, what do I do with this? I've never seen an equation with these parameters before, but it doesn't matter. My equation isn't a function of my parameters, it's a function of my words, which is right here. The final position, which I call gamma sub f, is equal to the initial position, which I called gamma sub I, plus the velocity, which I've called phi sub gamma, times the time interval, which I've called tau. And so the final is negative 1,240. The initial is negative 1,000 plus my velocity, which is negative 6 times the time interval tau. So add 1,000 to each side, and I get negative 240 is equal to negative 6 tau. Divide both sides by negative 6, and tau is equal to 40. The time interval is 40 seconds, which is the same we get the natural world. Physics doesn't care what you call your coordinate system and what you call your parameters. The answer is the same. And so your origin of your coordinate system, you get to choose. The direction of your coordinate system, you get to choose. What you call your coordinate system, you get to choose. What you call your parameters, you get to choose. What you don't get to choose is the physical laws. And it's most useful to remember those physical laws in terms of the words of the relationships between the physical quantities. And then you can use any equation you want.